We're starting out with, well, it's the quantum mechanics assignment, and it's the one that wants you to plot the, let's see if I can find it here, plot the Planck distribution. So, and the date, I mean, it's old, right, 2017, but it's the same assignment question because they're pertinent for you to know what you have to do. So this is called the, what's the official name? It's called the density of states. And what's interesting is that little weird looking, the units of it, and I'm looking here, would be joule per meter to the fourth. So they're calling it the density of states. So it's joules per meter to the fourth. So let's just take a look for a second here. When you look it up, in I think it's chapter 7 right now, but many books have this. The Planck distribution is very famous. Your job is, as a math exercise, to simply show how to plot this in Excel. So the couple of things we notice is this. You can have, at a higher temperature, kind of goes like that. At a lower temperature heads this way, right? So the higher the temperature, the closer you get a higher concentration, if you will. And this is the wavelength, right? I don't know, usually in like nanometers or something like that. And the energy distribution or the energy density of states, rho, is here. So this is in joules per meter to the fourth. And let's say that we make this in meters, just to keep it simple. So one of the things they used to be obsessed with, and you know that the energy density, so one of the equations for that is the energy density, and they use the funny looking E. They don't want to use E for pure energy because this is the actual energy density. And what that means is when you calculate this, you will get joules per cubic meter. So they pick a volume inside of something, and they look at the energy density, funny looking E, as opposed to just normal E, which would be just joules. And it's equal to rho d lambda. Now think about this. What this is telling me is if I integrate this side, funny E, and I integrate this side between wavelength 1 and wavelength 2. Think about what you're going to be calculating here. If I chose, say, this graph, and I call this wavelength 1 and wavelength 2. Isn't it pretty obvious that we always said this? What is between the integral and your d whatever variable, this is your x-axis, lambda. This is what's on the y-axis. So when rho, the energy density of states is what they're calling it, is your y. This integral is simply the area under the curve. So what they're basically saying is when this one integrates to the energy density, which will be in units of joules per cubic meter, this will be the area under that curve. And we all know that the area under the curve, this one, rho, has units of density per meter to the fourth, and units of d lambda would be in that. So it's pretty obvious. The area under the curve gives you the energy per cubic meter at this wavelength. But don't forget how this started. This is the classic, you know, they had this giant metallic, you know, thick black box, if you will. And what they would do is, monstrous oven, if you will. Let's say they put it at 1,000 Kelvin. And the idea was they would set up a detector right here, and it's measuring the intensity or the measure of energy, the intensity of energy coming out of it at a particular wavelength. You can almost view it in today's day and age where they could say at each wavelength as they scan, as the wavelength gets smaller, it's higher and higher in energy. So imagine, if you will, a more sensitive detector that could pick up all of the photons, okay, hitting the detector. So at one temperature, they can see that the number of photons they're getting, if you will, is, and this is what rho, is proportional to the number of photons hitting the detector. So what they realize is that they get to smaller and smaller wavelengths. When you start getting to the wavelengths that approach X-ray or gamma rays, this drops to almost none, meaning that nothing coming out of here is in the X-ray or gamma ray wavelength. No photons are coming out of it like that. And even when they jack this up to 10,000 Kelvin, you might get a larger proportion of photons, and this is sort of the UV range. But when you get closer to this range here of X-ray and gamma rays, they're not detecting any photons coming out of this black box. But think about it, folks. When you heat the crap out of this, all of the molecules and atoms that make this up, no matter how much energy gets exchanged in here, they can only go to excited states that are UV or very low level X-ray. You'll never get high energy X-rays or gamma rays coming out of something just because you're heating at a higher temperature. And that's why the number of photons coming out of here hitting the detector at X-ray or gamma rays has to drop to none. This is what they call the ultraviolet catastrophe, because back then they couldn't understand what we know now. The energy states of the actual atoms or molecules making this up, they can only undergo typically UV or visible and towards the shorter wavelengths. We can measure those photons coming out very specifically. So that's what this graph is all about. That's what this energy density is. So in other words, what they're saying is, if they went inside this box, and let's say this was a giant box, let's say it was 10 cubic meters or 1 cubic meter, right? They're going to calculate the joules of energy coming out at the wavelengths here. So the area under the curve would be the total energy per cubic meter of these wavelengths, right? So I think you can see how that works. So that's kind of how that makes sense. The other thing we have to do for this question is, when you go back to this formula, all you have to do is graph this. So this is your y, right? And your x, so why don't I redraw this? Your x is wavelength. So if you have, think of it this way. Rho equals 8 pi hc over wavelength to the 5th times 1 over e to the hc over wavelength Boltzmann's constant t, and it's minus 1 up in the exponent, right? What if I said in math class, what if they said, correct me if I'm wrong, Planck's constant, c is a constant, so couldn't I replace this in math class with some giant constant, just call it a? This is x to the 5th, right? Now you're multiplying it by hc kt right there at one value of temperature. This would be a constant. I could call it constant b, and that would be e constant b over x minus 1. So in other words, you have it's almost like two functions. Anybody could graph y equals a over x to the 5th, but what you would have to do is multiply that value by whatever this is, e to the b over x, if you will. So this is kind of the idea of what you're playing with in math class. So I would argue, if you're going to put this in a spreadsheet, probably a good idea to come up with what does 8 pi hc equal as a number, once I have that number, I could put it in my Excel spreadsheet rather than type all this stuff in one thing. The other thing, this is a good point I want you to know, in Excel, and this is what I did, I went looking for the e to the x function in Excel, but I came to the realization, and I'm gonna look it up here. You can get your calculator. We know that e stands for a number raised to the exponent, and I know that in Excel I can take any number. Like, for instance, all I have to do is use this funny symbol and put it, for instance, to the fourth. So if you type in e upward fourth in Excel, you're going to get 2 to the fourth, which equals 16. But what is e? So why don't I put in my calculator e to the 1? So I go to my calculator and I'm going to say second function e to the 1. So there you have it. So e is literally 2.71828. So what I did in my Excel spreadsheet is I used the value of 2.71828 as my e. So I typed that number and then I used that funny, put it to the exponent of whatever I needed, which was this stuff. So that's one little note. The other thing I can point out is, let me pick one here, and I'm actually going to bring up my spreadsheet. And what do I have here? So for instance, what I can tell you, you should check your calculation first. So rho equals 8 pi Planck's constant c, and that's wavelength to the fifth. Then you're going to multiply it by 1 over e hc wavelength kt minus 1. So what I've got cooking here, first of all, this, I believe, you have to check this. When you multiply this stuff out, I'm getting 4.98836 times 10 minus 24. And you know that the units, and I'm going to let you guys do this. First of all, this right here has to be unitless. You can't have e to a number with units. So this thing, this mess, is supposed to come out with units which we already know has to be joules to the meters to the fourth. So I'll let you work that out yourself. But that's the numerical number I get for that. And yeah. So if you have rho, and let me pick here just to give you a number, 1,000 Kelvin. So if your temperature is 1,000 Kelvin, then your value of rho for a wavelength of 100, now that might be nanometers, but you're going to have to convert that 1 times 10 to the minus 7 meters. The value I get for this, when all this is said and done, I'm getting 100 nanometers. I got to make sure I get this right. 1.7704 times 10 to the minus 51. This amounts to a number check. You can tell if your Excel spreadsheet has done this right for you. If for 1,000 Kelvin, so T is 1,000 Kelvin, you put in 100 nanometers, but make sure you put it into meters first. When you plug it all into this, and Excel is calculating it right for you, the value of rho better come out to be this value. 100, yeah, that's 1,000. Okay, so now what I'm going to do is I'm going to take this out of the retort stand here, and we're going to take a quick look at just an example. I normally show this in class. So you can see what I've done. I take a nanometers and I put it into meters. I then put it to the fifth because we know the formula needs it, right? So then I have in this one, what is the value of HC over the wavelength KT? So what does that look like inside the cell. So what I've done, you can see I got Planck's constant in there. Speed of speed c. B4 is wavelengths to the fifth, and that is Planck's constant times t. So that's pretty self-explanatory that I've just calculated the entity, right, hc, in that I've got this value ready right there, right? So then to calculate rho and its total, I already know that this number will be divided by this to the fifth. Then you're going to multiply it by 1 over e to the value I just calculated minus 1 in the exponent. So let's just take a quick look. So rho at 1,000. This is how you can do this many different ways. And this was over here for the 50, right? So if I click on rho, what mess did I put in here? Well, I'm going to have to double check that. I've got to double check that. So we're going to back that up. All right, we're back in business, folks. I've seen so many spreadsheets. I just had to get my head straight here. So obviously, I've got wavelength to the fifth, which is this one, c, looks like 4. That'll be for the exponent part. So when we click here, and I look at how I calculated this, yeah, that's right. So C4 was already the wavelength to the fifth. Right, so that's why I was correct. This was to the 24th. I'm going to divide by what my spreadsheet had a column for the wavelength to the fifth, so I'm dividing it by that. Then we're going to multiply by this jazz. And what I put in place of E was that number I showed you, the base unit of this. That's how I chose to do it. So I did not use the e to the x function in Excel because I just used 2.718. So let's see how this plays out. And I think you can see it. So there's that constant divided by this. And notice how I bracketed in, and this is interesting, I bracketed in the C4, which is your wavelength to the fifth, times E to what D4 is, which D4 was that exponent part pre-calculated, right? Subtract the 1. When you're doing this in Excel, folks, and this is what's interesting, the slightest thing of a bracket and another bracket, like I've gotten here in this division, you have to pay very careful attention to that. So let me just reiterate. It's up to you. You know the wavelength in nanometers. I already gave you the 100 one, right? Put it in meters. I elected to set my spreadsheet up this way, but the long story short is I don't care how you do it. When you calculate your value for rho, that's the number it has to be at 100 nanometers when you're at 1,000 Kelvin, right? So however you spread it up, this is what it should look like. Now, how do you know you've done this right in the long run? When you copy and paste, and let's just go to 1,000. So I'm going to scroll down. Here is 1,000. So let's bring this bigger. Now, why did I say don't try and fit this with a curve? What you're supposed to do is populate more and more little calculated results. So right where you see the curve, you put more results so you can see with your own eye what the shape of the curve looks like at 1,000 Kelvin. That's the point. Now, for 1,000 Kelvin, you'll notice that, look at this. The wavelengths of 0 to almost 1,000, it might as well be 0. It doesn't take off until 1,000 nanometers, right? But if you move on to 1,500, what you notice is the higher the temperature, before you get to 1,000, see how it starts to take off. So the higher the temperature, the more data points you'll have to have down at lower wavelengths, right? And this one peaks at obviously, one wavelength here. Now what you're supposed, so you put in enough data points in your spreadsheet so you can see it with dots by eye. And then you're supposed to, absolutely, you're supposed to, and I got to get rid, see, this is the problem with Excel. I got to shrink these damn things and drag them out of the way to clear up the one I want to look like, or I want to look at. So here is the one that has all of them. This is what you have to produce. So clearly, the highest temperature, 2500, is this one. It has the highest intensity, and it has values at the lowest wavelengths, right? Your higher temperature, the 1000, looks almost like a flat line compared to the 2500. And notice how the maxima is shifting to higher and higher wavelengths, and it's getting spread out more. So this is what you're shooting for. You obviously know you've done it right if this is the pattern you get. This is what you're handing in, right? So that pretty much sums it up for question 1.